Now in this video I'm gonna be explaining another important article about relation extraction, which is this paper in 2019, and this is a positive sample. So this paper, regularizing discriminative approaches with relation distribution losses. In a supervised setting, discriminative approaches such as deep neural network classifiers have demonstrated substantial improvement. However, these models are hard to train without supervision, and the currently proposed solutions are unstable. To overcome this limitation, we introduce a skewness loss, which encourages the classifier to predict a relation with confidence given a sentence, and a distribution distance loss enforcing that all relations are predicted in average. So unsupervised relation extraction models is interesting for three reasons. Then they do not necessitate labeled data except for validating the models. They can uncover new relation types. When we say new relation types, we sometimes think about zero-shot learning. And finally, they can be trained from large unlabeled data sets and then fine-tuned for specific relations. So our model focuses on extracting the relation between the two entities in textual data and assumes that a recognition tool has identified named entities in the text. So we have two entities, and then we identify them, and whatever before that entity 1 is prefix, whatever inside entity 1 and 2 is called infix, and whatever is after entity 2 we call it suffix. So if we just augment them, this is what we mean by S. To provide a supervision signal to our relation classifier, for example, the soul was currently of, so we suppose we want to first learn that this sentence expresses the semantic relation currency used by. Before using this information for a supervised test, so we suppose that the relation can be predicted by text surrounding the two entities, and we just need the surrounding thing, and we don't need the entities. We then try to predict the missing entity given the predicted relation and the other entity. So this makes it a supervised learning. So first we do relation classifier. For example, given a sentence, that sentence that is augmented like prefix and then suffix and those things. And then we predict the relation. But the entity that we want to predict, if we know one of the entities, if we know the sentence, we could predict the next one. So that's why this is a supervision signal that we need for supervised learning. So the prediction of relation given your sentence, and by sentence we mean just prefix and infix and suffix. We give it a convolution, and what we get is this prediction. But your prediction of entity given your relation, and one of the entities could be represented by such energy-based approach. So we say there exists some function, we call this energy associated with entity 1, relation, and entity 2. And so we can decouple that using, for example, say some of them are this term for entity 1, some of them is related entity 2, and some of them is mixed. So the number of entities being very large. Just like the problem of word2vec, we had lots of things. So we used negative sampling in word2vec and many other problems that we have lots of classes, huge number of classes. Another alternative could be, for example, hierarchical softmax. Another alternative could be, for example, contrastive loss, which are adversarial things to discover if it is noise or it is data. So there are three major approaches to deal with this. So in this article, it just uses negative sampling as one of the three approaches that I just mentioned. So to avoid the summation over the set of entities, we follow Titov and use negative sampling. Instead of training a softmax classifier, we train a discriminator, which tries to recognize real triplets, if it is real or it is fake. So sigma here is just the sigmoid function, and this model is then trained by generating negative entities for each position and optimizing the negative log likelihood. So this loss is defined over the data distribution. This is your data distribution. And the samples follow a uniform distribution over sentences tagged with two entities. The distribution of the relation for the sentence is then given by the classifier, which corresponds to this sum of, because you have lots of relations, and you get, so the expectation of negative entities is approximated by just sampling k random entities. Training a classifier through equation 3, this one, is very unstable and dependent on precise hyperparameter tuning. More precisely, according to our early experiments, the training process usually collapses into one of two regimes. Either the classifier is very uncertain about which relation is expressed and outputs a relation following a uniform distribution, or the other regime, which also sentences are classified as conveying the same relation. This is a classical problem in contrastive learning when you want to do, for example, CMEs and network. Everything collapses to a particular constant. And there are, of course, methods for that, such as stock gradient method. So if you watch my playlist on contrastive learning and CMEs and network, I explain all of these paradigms. Skewness. So to encourage the classifier to be confident in its output, we minimize the entropy of the predicted relation distribution. This addresses problem 1 by forcing the classifier toward outputting one-hot vectors using this. So this is the entropy of, and so entropy of a relation given your sentence. And the other one is dispersion. Secondly, to ensure that the classifier predicts several relations, we minimize the KL divergence between the prior and the uniform distribution. Note that contrary to L of S, which for skewness, in order to have a good approximation for P, the loss measures the unconditional distribution and the distribution of predicted relations over all sentences. This addresses P2 by forcing the classifier toward predicting each class equally often over a set of sentences. So to satisfactorily and jointly train the link predictor and the classifier, we use the two losses at the same time. So our final loss is just the sum of them. And these are hyperparameters you can tune. So we have a loss for link predictor, we have a loss for skewness, and we have a loss for dispersion. We train them jointly.